need to change this one. Maybe we need to put this one here. Right. It's important to. So can you see my screen online? Can you see it on Zoom? This screen? You can see it online. Okay. Okay, very good. So today it's today in fact it's because I got some questions from some people that we need to go to this error band propagation and we need to implement it, for example. It's not very important because anyway you will use the tools, but maybe it's important to understand the concept behind it. So today we will talk about basic numerical methods for training a machine learning method. We are using a gradient descent, for example. We can use gradient descent if we have a function, and if we need to minimize this function, for example, we need to find the value which will minimize it. It could be gradient ascent if we need to maximize. This gradient descent is a very smart approach, in fact, because we don't need to solve any problem numerically. We can we don't need to solve it in symbolical way, right? We don't need to find any analytical solution. So we can solve it numerically. So, of course, this is straightforward neural network. We have input layer. The input layer, it has nothing to do, in fact. It's just transferring the input signal to the first hidden layer. This is the hidden layer, for example. This is the output layer. Number of weights, now we can find number of parameters which we need to adjust. Number of weights will be number of inputs times number of units of hidden layer, and so on. In feed-forward neural network, in fact, which we need to discuss today, we go forward to calculate the output, and after that, we need to go backward to adjust the weights. So all time we do it like this. We go forward and we go backward. How many times we need to adjust? It's according to the learning approach. If it is stochastic gradient descent, we will for each example, we will update the weights. So we will update in each epoch. We will go through the data set one full time, going forward and going backwards, right? And then we will adjust the weights for each single example, if it is a stochastic gradient descent. In SCDG, it's good because of online learning, for example. So you can build your model, and you can later on, when you have some new data incoming in, you can just adjust your model for each single example. It's good for online learning. A batch gradient, it's a different approach. In batch gradient, we calculate the error gradient when we go forward for all examples, and we find the mean value, for example, of the gradient, and we adjust the weights only one time in each epoch. So, for example, if you have 100 data points, and you will run your model you will train it for 10 epochs, for example. In this case, it will be 10 times 100 times for updating the weights, correct? If it is a stochastic gradient descent, so it will be 1,000 times. We will adjust the weights 1,000 times. If you will go for batch gradient and the batch size will be, for example, 20. So in this case, we will adjust in each epoch, we will adjust the weights only 5 times. So if I will train my model for 10 epochs, it will be 5 times 10, it will be 50. So many batch gradient, it's something in between. So because, in batch gradient, we use the whole data set. In batch gradient, we use the whole data set. We go forward, we will calculate the gradient for the whole data set, and then we will adjust only one time in each epoch. This is the batch gradient. So if you will train your model for 10 epoch, you will adjust the weights only 10 times, one time per each epoch, because it's batch gradient. In batch gradient, we use the whole data set, the whole training data set for calculating the average gradient, for example, and we adjust the weights only one time each epoch. Many batch gradient, it's in between. So this is what I mentioned, 50 times, for example, if the batch size will be 20, and if you have 100 data points, and if you will train your model for 10 epochs. So this is the difference. How can we decide? You can decide based on the hardware which you have, for example. Right? So it's a known when we use the average gradient, for example, we will move smoothly, and maybe it will help us to avoid some local minima, for example, right? But it's according to the hardware, according to the memory which you have. Because when it's batch gradient, we need to keep all those calculations in the memory. We need to keep all data points in the memory. So maybe it's not possible. So in this case, you can just say, okay, I will go for batch gradient. Batch gradient, we will control the size of the batch size according to the memory which we have. So of course, we can implement it, but later on, you will use the packages which we have already in Python, in Keras or sklearn or PyTorch, for example. They are very good in doing this. But it's important to just understand what is happening behind the scene or in the back end, for example. So today we will talk about gradient descent. We'll talk about it already and we'll talk some examples, right? Do you remember? But we can talk about it one more time. We will try to apply this for gradient descent for 1D and 2D functions. 1D, for example, fx equal x squared, and we need to minimize it, right? So it could be an example for example, an error back propagation algorithm. We need to talk about it because when it's a neural network, the cost function will be very complex. The cost function, which is E equal, so we have this cost function, error, equal half this summation, t minus y squared. This is a function which I equal 1 to, for example, n. So this is a function which we need to minimize. We need to find the weight which will minimize this function. So we will use gradient descent for doing it. We will use the function which I implemented here because I implemented it just in a very simple way, error back propagation for a neural network with one hidden layer and with one output layer. I just made it simple. But if you want to make it complex, you can just make some modifications and you can make it more complex. And I will use it for classifying iris datasets, just to check if the algorithm is working or not. So we can start with machine learning algorithm are implemented on computers and mathematical formulations are expressed as numerical optimization methods. We do it numerically. So we do differentiation numerically, we adjust weights numerically, but in fact, you can do it analytically if the function is simple. So for example, if I have a simple function like this one, f of x, for example, equal x squared, so we know how to minimize it numerically. So we need to get the first derivative, we call it f dash, for example, 2x. We will equate this one to, we will set this one equal to 0. So now we know that x equals 0. We can just say this is x star equals 0. X star equals 0, this is the value which will minimize this function. So in fact, this function is minimum at x equals 0, correct? And when we plot it, it will be like this one. So this is my function. We plot it against x, and we have here f of x. So it will be in fact minimum here, right? It will be minimum at that point. In gradient descent, it's very simple. We start from some point in random, but we need to calculate the gradient. The gradient will be this function, f dash. So we do it like this one. So delta x will be, do you remember? Huh? Do you remember the formula? Delta x equal? Yeah, delta x equal? Do you remember delta omega? Do you remember this one? Online, can you remember what was delta omega? Maybe you cannot see my screen. I will try to make it. We will fix the camera, but I mean, things takes time. And I don't know. Oh, okay. Yes, I don't know. Maybe you cannot see it. But so do you know the formula for this one, delta omega? What was delta omega? Negative. Do you remember? Negative eta multiplied by gradient, partial e by partial omega. So this is the formula, right? So this value negative because it's we want to minimize, but it's not. It's because we are moving against the gradient. This one it's the learning rate multiplied by the gradient. So it's the same here. It will be also something like this one by partial f by partial x, which will be negative. This one it's 2x. So it will be 2 times eta or just eta x. Because 2 times eta, it's like eta, correct? 2 times the constant, it's constant. So this is the gradient. So now we need to move against the gradient. We start from some point here. Imagine that we're starting from here by random. Maybe this number is negative, right? So maybe it's -5, for example. And x after that, it will be x plus delta x, right? So imagine that the learning rate will be 0.5, right? So this one will be minus 0.5x, correct? And in the gradient descent algorithm, we start by random value. I will select this point by random. I will calculate the gradient at -5. So it will be -5 times -4.5. So it will be 2.5 delta x, correct? So in this case, I need to update x. So x equal -5 plus delta x, it will be 2.5. So it will be -2.5. So now the next value will be -2.5. It will be a value here, -2.5. So now we are moving. Do you see how much? So we moved it to this point. I started here. Now we are moving to this point. We are close. So next time, I will do it one more time. So the next time we need to calculate the delta x, new delta x. So it will be -0.5 times x minus 0.5 times -2.5. So it will be 1.25. You see? It's still plus because we are moving against the gradient. So the new x value will be the old, which is -2.5, plus the new one, which is 1. So now it will be plus, it will be -1.25. Now we are moving one more step, right? So now we move to the next point, which is here. So we are here now, -1.25. So we will move step by step until we reach the minimum value. So this approach is a very good approach. But it's very important is that the function is convex. And that is why we squared this error function, because we want the function to be convex. And when it's convex, we will be sure that we will reach the bottom. Maybe this bottom is a local minimum or global minimum. If it is local minimum, it's catastrophic because there is no way to avoid it. We can use momentum term, we try to avoid it, but there is no guarantee, in fact, that you will avoid it, right? Because this function looks very nice, but if the function looks like this, so what will happen? If we started by chance, right? If we started from that point, we will be lucky because we will reach this one. This one, it's local, it's a global minimum. But if we are here, maybe we will stop here, right? So there is no guarantee, in fact. It's like in optimization algorithms, stochastic approaches. There is no guarantee that you will reach the optimum one. We will reach an optimized solution, but not optimum one. Because optimum, it's, I mean, مطلق يعني مطلق. Absolute. It will not absolute minimum, right? But it's maybe we will stop here, right? How can we avoid this one? Maybe we can use momentum term. The momentum term will have more energy to try to skip from this one, but also there is no guarantee effect, right? So this is how the function working. So training a machine learning model often boils down to finding a good set of parameters. We try to find the good set of parameters. In this sample function, we have only one parameter, we have x. But when it's a neural network, we have omega, right? And it's more complex. So when we have a feed-forward neural network, imagine that we have one hidden layer, one output layer, two inputs. So it will be really more complex. You see, it will be something, maybe it will be impossible even to plot it. I mean, we can plot it with the error surface, of course. So we have x1 and x2. We have this one, omega 1, 1, omega 1, 2, omega 1, 3, omega 2, 1, omega 2, 2, omega 2, 3. We have V1, V2, for example, V3. We have bias values. So this one is very complex. We need to find a set of omega and a set of B, which will minimize the cost function. So it's not easy task. It's very complex.
Ibrahim,
yeah.
I just got a question.
Yes.
So by parameters, do you mean the weights or do you mean the inputs? What do parameters?
No, the parameters are the weights, right? The parameters which we need to find are the weights, not the inputs. The inputs, it's a signal which we are getting from outside, so we can do nothing about it because this is the input.
Okay, right? Got it. So by parameters, you mean it's just the weights. It's not even the learning rate, and it's not even the other inputs that we give.
No, not learning rate. Learning rate, it's hyperparameter we need to select, right? So it's also okay, hyperparameter which you can optimize. You can select from different values, right? But the learning rate, it's a hyperparameter. It's not a learnable parameter. It's not a parameter which can be used to. But because at the end, Do you see this function, error function? It's function of target minus output. The target is the input. So this one, in fact, this one it's the input. So it's constant. It's something from outside. It's an input to my model. So it's constant. It could be an image. It could be number. If we are working with banking system, it could be age and the income. And those numbers, we can do nothing about it. But this is the case here, Y. So Y, it's the activation function, which is function of omega. If we are using sigmoid, so Y will be 1 divided by 1 plus exponential minus omega x plus b. So do you see, this is omega and this is b. Those are the parameters which we need to minimize. So if imagine that you are using sigmoid and imagine that you are using a perceptron or whatever. So Y will be 1 divided by 1 plus exponential minus omega x plus b. So this function, in fact, it's function of omega or function of those parameters, omega and b. We need to find a good combination of omega and b, which will minimize this error function. So this is the task. So when I mean the training process, it will be boiled down at finding a good set of parameters of omega and b, which will minimize this cost function E, right? So the loss function, which we try to, because at the end, I want my model to learn, the inputs, correct? How can we do this? By minimizing the difference between the target and the output, right? At the beginning of the year, for example, before we're studying the course, for example, we have a target. We need to study this and this and that, correct? And this is the output. So the whole task during the whole semester, for example, is to minimize the difference between what we are planning and what we know already. So this is the case. So how can we adjust this? We need to find a good set of parameters, omega and b, which will minimize this cost function. So this is the whole task. So you can just compare it with this simple function, f of x equal x squared. This function, it's a sample, it's function of x. But this error function, it's more complex and it's multidimensional because it's function of omega 1, omega 2, omega 3, omega 4, omega 5, b1, b2, b3, b4, b5. It could be function of millions of parameters. So when we study deep learning, for example, maybe my model has 1 million parameter, right? So my function will be function of 1 million. We need to adjust those weight values. How can we adjust it? Using this gradient descent approach. Is it clear? So the convex objective function ensures the statement of reaching the global optimum. We need to reach the global optimum because if you have this function, for example, you have some. I know that any cost function will be bumpy like this one. It will be more complex. It's not simple. But just imagine that we hope that we have a cost function which is convex like this one, because if it is like this one, if you run your algorithm 100 times, you will reach the same solution. Right? If the convex function is simple, you will get this solution. But sometimes he runs a code, and each time when he starts from different random value, and he cannot reach the same solution. Why? Because of this one, right? If it is convex and it's simple like this one, we will reach this one infinite. If I started from this point, I will reach it. If I started from this point, I will reach this point. Maybe just number of blocks, correct? But we will reach this solution. But sometimes you run your code, if you don't have a fixed random seed, for example. So each time, one point I will start from here, so I will start here. Someone else, he will start from here, he will reach this one. The solution here, it's much better than this one.
But the first ones are just local minima. This is the...
No, this one, it's a global minimum anyway. We will reach this point because it's a very simple one. But this one, it's a local minimum. This one, it's a global minimum.
And what is global optimum?
This one. This is the global optimum. So we need to reach this point, not this one. But maybe you will stop here. No one knows. You need to run your code maybe several times until you reach this point or change the model hyperparameters. So maybe we will add the momentum term and we will change the momentum factor because I need to get out from this one, right? Because this is the dilemma effect. Even in optimization algorithm, if you are using a genetic algorithm, for example, there is no guarantee that you will not start here. Correct? Because it's heuristic, and there's a problem. If we stop in one of those points, we will stay there. It will be very difficult, in fact, to get out of it. So when it's a local minimum, it's a solution. We cannot improve it anymore, but it's not the optimum solution. We call it optimized solution. So one of the good solution, it's a good solution anyway, but it's not the best solution. If we can reach this point, how can we reach this one? We can reach this one by solving the problem analytically, in fact, not numerically. Because when we solve it, we will find points which are minimum, and we can differentiate between local minimum and the global minimum, in fact. So if we are solving it analytically, we will be sure that we will guarantee that we will reach the global minimum and we will get an optimum solution. But when you are solving it numerically, there is no guarantee. And it's a mistake to call it optimum. You cannot say optimum. So if you are writing a paper, try to avoid the word optimum, because optimum, it's a global optimum. People will just say, no, how did you know that this one is global optimum? It's not optimum. It's more professional to just say it's an optimized solution. Optimized means it's one of the good solutions, but it's not global optimum, not absolute minimum, for example, or absolute optimum. Yes. So this is an example. Yes.
Ibrahim, sorry for the interruption. Like, can you move the laptop or a bit closer to the screen? I mean, the blackboard, because whatever, it's not very visible to us on.
Yes, I wish to do this, in fact, but
is it, this is, I think, fine.
Is it different?
Is
it?
It's not really, I don't know.
Sorry for, but we have camera. We have two cameras in the classroom, but I mean the company.
Okay, yeah, this is fine. This is okay. I think this is. Is it right? Like, can somebody else confirm?
Yes, maybe you can get this one here. Is it much better?
Yeah, now it is better.
Okay.
You can see you now.
Yes. Yes. So I mean, so if you can look, I mean, if you can see in the screen here, we have this function. It's also it's 1D also. I mean, it's x4 and x cubed squared, but at the end also it's function of x, and we need to find the value of x, which will minimize this function. So in fact, in this plot here, so in fact, the green one, it is a function, correct? Which we try to minimize. So this is my function. And we try to solve it analytically, in fact, because we try to solve it analytically. So we'll get the first derivative. We will set the first derivative equal 0. When we do this, we can find the three values. You know, now it's more complex. Now it's more complex. I mean, this is my function, and minus 4.5. Yes. So the blue one, I guess the blue one, it's a function, right? The blue one, it's my function, and it has some global minimum, and it's maximum, right? And it's local minimum. So this blue function, do you see the blue function? When we got the first derivative, we have three locations. It's like it's a proposed locations for global minimum or maximum, right? When we get the first derivative and put it equal 0, we got those x values, three values, minus 4.5, 0.7, minus 1.4. But I don't know which one is maximum, which one is minimum, right? Which one is global minimum, which one is local minimum. This is how we can. So I plot here the first derivative. I plot here this green one, in fact, maybe this is the first derivative, and the red one, it is the second derivative. I will go into the second derivative. So this one here, you just need to check each point if the second derivative was positive or negative, right? And we can find that this point here, it's a minimum, because the second derivative, in fact, is positive, right? So just to check those points. So when the second derivative is positive, it means it's minimum. I mean the function will be minimum at that point. So it will be minimum at that point. At that point here also it will be positive. No, it will be negative here, which means this is maximum. So when the second derivative is, it is a opposite. So when the second derivative is positive, it means this point is minimum. When the second derivative is negative, it means it's maximum. So the second derivative at that point is negative. I mean this function is negative, which means this point is maximum. And the other point also it's positive, which means it's minimum. So the function will be minimum at those 2 points. So now we have 2 points where at which the function is minimum. We need to know which one is global minimum, which one is local minimum. So it's according to the value of the second derivative, right? So when it's more positive here, it means the function is, this is the global minimum, right? So we assume that the function to be minimized, f is differentiable. Very important that the function is differentiable because we need to calculate the gradient. So it's the same way here. I mean, this function is differentiable. So in fact, it's very important to select the activation function, which is easy to get the first derivative because the function must be differentiable. So when we are selecting the activation function, we can just come up with any activation function. The most important is to know how to differentiate this activation function because we need to find the gradient. So we assume that the function to be minimized is differentiable, and we are unable to analytically find a solution in a closed form. We use numerical approach when it's really more complex to solve it analytically, because when you solve it analytically, you will get absolute values. But when we solve it numerically, we will get approximate solution, right? Because each time I can differentiate, I can select a different learning rate or starting from different random value. So we try to reach a good solution as much as possible. But if you can solve it analytically, it's fine. But it's impossible to solve in deep learning or in feed-forward neural network. It's impossible to solve this function analytically. So we solve it numerically. To find a local minimum of a function using a gradient descent, one takes steps proportional to the negative of the gradient. So, I mean, those steps, I mean, we change x by a step. This step will be negatively proportional to the gradient. So we multiply by negative all time, right? Multiply by negative. We have here constant. This constant value, this is the step rate or step size for the learning rate, for example. One takes steps proportional to the negative of the gradient of the function at the current point. We start with an initial guess x0. This one is initial x0 of the parameters we wish to optimize, and then iterate according to this equation. So we just take it step by step, and we start by an initial guess or just a random value. We just make it simple, just select a random value. Or start from 0, for example, no problem. Start from 0, right? Or start from any small random value. So xi plus 1 equal xi plus delta x. So delta x now equal minus eta multiplied by the gradient, partial f by partial x. By partial xi, because we will do this one for each weight value for each parameter. Maybe your function, it's a function of x1 and x2 and x3. So we need to do it for partial f by partial x1, partial f by partial x2, because I need to change x1, x2, x3. We will do it one by one, right? So this is how we do it in neural network. We do it one by one. So I just implemented, if you can go to Python or Colab and try to implement this one, we can do it now, right? So just open your Colab and try to implement this function. I have the code here. So this is the function. I just defined a function f of x, right? And I find the first derivative. It's very important to have the first derivative. We need to have a function which can be differentiated. And after that, we need to define the learning rate. We need to define the learning rate and the number of iterations, and just do it in a for loop or a while loop, for example. I put it in a for. So x equal x minus eta multiplied by delta f by delta x. But in fact, this one alpha, this is the momentum term if you want to add momentum term. So momentum term, it will be constant multiplied by it's delta x. You can call it delta x alpha plus delta x. It's it's current x minus last x, previous one. And I just run it from, as I told you, as we are expecting, this is a function, and this function has global minimum. This one, it's a global minimum, and this one, it's local minimum. And it's by chance. If you started from that location, we will be lucky and we will reach this value because this is the optimum solution for us, right? This one, it's not good solution because we're stuck here. And there is no way, in fact, to get out of this this one, right? So it's a problem. I mean, it's a problem. We need to, accept this. So it's according to the, starting point. When we start by random from different locations, if we are lucky, we will reach this point. If we are not lucky, we will stop here. This is the problem also of optimization, right? Because we solve optimization problem. I want to travel from here to Oslo, and I use optimization algorithm to select which way. Should I go by plane? Should I go by car? Should I go by bike, for example? So it's the same. If you are not lucky, you will get a solution here which is not the cheapest solution, or may not the fastest solution, for example. So we will get a solution. It's a good solution anyway, but maybe it's not the optimum solution. So can you go to Colab and try to implement it?
So, sorry, you said the solution that we get is the optimum. It's the optimum, not the global.
No, it's the optimum if this is a solution.
So when it is global minimum, it is optimum.
Yes, of course. When it's a global minimum, it's optimum.
Okay.
But when it's local minimum,
it's just optimized.
Sub-optimal, or you can just say it's an optimized solution. But in general, because you don't know, there is no guarantee. Right? So when you are solving a problem, don't claim at all that it's optimum. You can claim that it's optimum if you are solving it analytically. But if you are solving any problem numerically, so there's no guarantee.
Analytically, you mean?
Analytically means you have the function, you will solve it by just by getting differentiations and step by step until you get by mathematics, right? If you solve it by mathematics, it's an analytical solution. But when you solve it by computer, it's numerical solution. So when it's numerical, there's no guarantee that it's optimum. So when you are writing a paper, if you wrote that it's optimum solution, just to try it, you will get this comment from the reviewers. They will say, no, there's no guarantee, right? How can you claim that it's optimum? You cannot answer it, in fact. And this question is very important, even in PhD defense, in master thesis defense, because some people he provide a nice solution and he's happy with it. And he just say, yeah, okay, this is my optimum solution. No, just be careful, just say optimized. When you say optimized, you will give the people that you really are professional and you know the difference between optimum and optimized. So don't claim at all that it's an optimized solution. So online, can you do this code with us, please? Can you do it and go? You have also the code, in fact, in I just did it also in GitHub. If you want to go to it, but so this function, it's simple, in fact, but it will help us also to understand gradient descent and how gradient descent work. And yeah.
I was wondering, is alpha momentum or?
Momentum term. Yes,
Yeah.
Alpha is a momentum term.
Yeah.
Yeah. But also we need to, play with this alpha because, if I'm here, for example, right, and I need to jump here, I need very high value, correct? Maybe I need 20, very big value, in fact. So the momentum term also, this alpha, learning rate and momentum term, they are hyperparameters, which means you can just select any values. You can use grid search, for example, to try different combinations or different values. So one time I started from 2. I selected 2 here to start from 2 as a random value. I selected 2, for example, and you can select starting from -6, for example. When you start from -6, you reach global minimum, and when you start from +2, you reach a local minimum. I mean, in neural network, we will do the same, but instead of working with X, it will be omega 1, omega 2, omega 3, omega n, B1, B2, B3, Bn, for example. And instead of working with F, it will be the error function E, loss function, which we select. I mean, from this example also, what if the learning rate is too big? What will happen? We will come at some point here and we will oscillate. So instead of reaching this value, we can just oscillate across or around the minimum value. So we need to, usually people prefer to start with large learning rate, and when we are close to the minimum value, we reduce the learning rate. How can we do this? We can do it by the gradient. We can select the learning rate as a function of the gradient. At that point, what was the gradient value here? It was -5? No, it was -2.5 delta x. I mean this function, right? So it will 2 times x. When x -5, it's -10 in fact. So the gradient here was -10, correct? And at that point, -2.5. So -2.5 times, so it was -5. So this is a gradient, correct? At that point, it was -2.5. So the gradient decreased in fact until at that point here, the gradient will be 0 in fact. So do you see? So we're going from large value to small value. So we can select the learning rate as a function of the absolute value of the gradient, correct? So it could be, for example, 10% of this one. So when it's 10% of 10, we will start by 1. Here it will be 0.5. So it will be smaller. So you can just, they call it adaptive learning rate. So adaptive learning rate, it's a function of the gradient, right? Because the gradient, we start with a very high value and we are reaching the global minimum or local minimum, right? The gradient will become 0, right? So it will be function of, so here I selected eta, fixed value, right? But you can just select eta as a function of the gradient, and you can just make comparisons. Mm-hmm. So did you make it? Is it working with you? Okay, very good. So what is your solution? Is it the same? Can you make some changes? Can you select? Can you use this adaptive learning rate, for example? So adaptive learning rate, instead of, in this example, I selected eta as constant value from the beginning, but we can select it as a function of the gradient. So it could be function of the gradient. I mean, the gradient here, it's -10, -5, -2.5, and 0. So we start with larger value until we reach the global minimum, and it becomes 0. So you can just select the adaptive learning rate, for example. So you can say it's 10% of absolute value of the gradient, right? So eta will be, so we just need to add one line here. So eta equal another constant, right? 10%, 0.1 or 0.2 times absolute value of the gradient. And the gradient, it's the first derivative, this function. You can just make comparisons. So in fact, you can do a lot. I mean, working with those simple. In this case, we will start with a larger step, and when we are closer to the global minimum, I mean, the step will be very, very small. It will take more time, but maybe the performance will be much better. Because if you selected a large learning rate, maybe we will oscillate across the global minimum. So I did it also for, a function, 2D function. When it's 2D function, it's function of x1 and x2. So we will do the same, right? We will do the same, but we will do it for each variable. So we will do it first for x1. So x1 equal x1 minus eta multiplied by the first derivative. This one is a gradient for x1. This one it's partial f by partial x1, right? So we can try this function. So here we have more complex function. So now we have a function which is more complex. So it's a function of x1 and x2. It's more complex function, as you can see here, and this is the first derivative. So this is the function, and I need now to it's function of x1 and x2. So x1 will be x1 plus delta x1. 1 will be minus eta multiplied by partial f by partial x1. Right? For x2 equal x2 plus delta x2 equal minus eta partial f by partial x2. So we will do the same in feed-forward neural network. We will do it. We need to find the gradient for each weight value. We need to find partial e by partial omega 1, partial e by partial omega 2. So if you need to adjust a weight, we need to find partial e by partial z weight. So in each in the while loop, for example, we need to do this 4 steps or 2 steps, 2 updates, right? We need to do those 2 updates. So it's the same. It will be while iterations less than maximum iterations. X1 will be x1 minus eta multiplied by the first derivative for x1. This one for x2, right? It's different. The function is different. And we will just plot it. So we plot it in 2-dimensional space. This is the function, and we start from any random value. We started from that point, and we will do it step by step until we reach global minimum. So the approach, it works. But when we do it for simple functions like this one, f1 and 2D function or 1D function, for example, it's easy to visualize it. But for our neural network, it's more complex. Even for a very simple one, it's really very, very complex. But you can do it. You can do perceptron, this multi-layer perceptron, for example, from sklearn, and you can try to plot this graph, right? The error function. How can we plot the error function? It will be very nice. We will see lots of funny things. So this is how the function will be working. If it is feed-forward neural network, this one in 2-dimensional space, so it's easy to visualize it. So imagine you have a model with 40 parameters. How can we plot it? If we need to visualize it, we need to plot it in 40-dimensional space, which is impossible for us. So this is a problem. When it's a feed-forward neural network, it will be impossible to visualize the error surface. How can we plot it? It will be impossible. I can plot it for omega 1 and omega 2 because I can see it in 2-dimensional space. And each time I can find another combinations, omega 1, omega 2, omega 3, omega 4, and so on. But it will be impossible. You can just imagine how it will look like. It will be really something very, very tough to visualize. So they like to, this function also here, it's a gradient descent in 2D. If you want to get this one. So online, do you have any questions? Any questions for this 2D function? So we did that for 1D function and 2D function. So in case of 2D function, we need to calculate the gradient for x1 and for x2 and update x1 and update x2. Of course, in feed-forward neural network, life will be much easier because we can do this in matrix notation. I don't need to have one line for each parameter. So I don't need to adjust omega 1 and after that omega 2, omega 3, omega 4. No, I can just deal with it as in matrix notations. And when it's in matrix notation, it will be much easier. And that is why they arranged feed-forward neural network in layers. When it's in layers, it will be easy for calculations. Even to go forward, it will be matrix multiplication. To go backward, also it will be matrix multiplications. It will be much, much easier. So we can update the weights of each layer in one step. I don't need to do it one by one as we did it here, right? This one, it's more complex because I need to do it for each parameter. But I can do it in one line if we can use matrix notation, because this one is a vector, in fact. So I can calculate this vector and I can adjust the weights in one line. So, gradient descent with momentum term. This momentum term is very important. This momentum term, it's very important for convergence. So the convergence of gradient descent may be very small if the curvature of the optimization plot is such that there are regions that are poorly scaled. I mean, sometimes it's bumpy. So when it's bumpy like this one, I need momentum. I need someone to push me. It's like when you are you're driving all the car, for example, and it's bumpy. You just need someone to give me a push, right? So you need someone to push you. This momentum term, it will help you to get this force. To avoid this. So gradient descent with momentum is a method that is introduces an additional term to remember what happened in the previous iterations. So I need to get force from the previous iterations. This memory dampens oscillations and smoothes out the gradient updates. The momentum term emulates the phenomena of heavy pole that is reluctant to change directions. You just need to get some forces from, it's like a memory. So our algorithm, and without this momentum term, there is no memory in fact. So in each step, we just use current values and we don't have any memory. We don't remember anything from the past. If you want to get some memory, I need to get this delta x. Delta x, it's current x minus previous one. So it's like rate of change. It's like acceleration. So we just need to memorize what happened in the previous step. If it was very high, I will get advantage from this high value. And I will use this force to just help me to cross this local minimum and try to avoid it. And we can play a lot with this one. So you can just say delta x, it's xi minus 1. So it's last x minus. So I can play with those I and I minus 1, I minus 2. So if you want really to play with this one and just try to be creative and try to use historical value for. Yes, they can use historical value, in fact. I can use the last 10 values, and I can use the average of the last 10 values to help me. So the memory, we can control the size of the memory, how many steps we need to remember. So imagine this one, it's a delta x, it's rate of change, it's I minus xi minus 1. I can just replace it with the mean value of the last 10 steps, right? And I can use those values to just help me to just to push me forward when we have this local minimum. And it has a factor, and this factor, it should be number between 0 and 1, right? It's 0 when we don't need to remember anything from the history. It could be 1 when we need to have good memory and full force or momentum. So you can just control this one. If you will have this one in your algorithm also, it will be a hyperparameter. When it's hyperparameter, there is no rule for selecting it. So it's problem by problem. We don't know. You can select 0.5 in this current problem. It will work with you. Maybe in another problem, 0.5 will not work. It should be 0.55 or 0.6 or 0.7. So it's a hyperparameter. So there is no rule, in fact, for selecting those hyperparameters. Right? Trial and error. You can just use an optimization algorithm for helping you to select best combination of those hyperparameters. And those hyperparameters, we have the validation set. We have the validation set for adjusting those hyperparameters. So when you decide the structure of your neural network, I have 2 hidden layers, and in each hidden layer I have 10 units, for example. So now we agreed on a structure of my neural network. I will train my neural network, but I don't know which good set of hyperparameters. So we can use the validation set to help me to select or tune or optimize the hyperparameter. right? Because once we select the structure of my neural network, we will stick to this design. But now I need to select the optimum set of hyperparameters. We can use the validation set for doing this. So my training set, we will divide it again. Do you remember? Hold out validation, and hold out validation, I divide my data set into one set for training and one set for testing. Maybe it's 20% or 30% for testing and 70% for training. Now we will go for the training part. The training data, we use it for adjusting the model parameters with values and the bias, correct? So, but what about the hyperparameters? How can I adjust the hyperparameters? If you need to adjust your hyperparameters, the training set, you need to hold out small part from it, maybe 10% or 20% for validation. So I will divide again the training set into one for training and one for validation. The training will be used for adjusting the weights, and the validation will be used for optimizing the hyperparameter, right? So I will use the training part for adjusting the weights for a set of hyperparameters. And I will validate my solution. I will check. It's like a test set for the training set, this validation part. So I will test using the validation. Is it okay? The performance is fine. So you will just use this validation set for testing, and you will get the accuracy, for example, and loss and all those numbers. And you will select another set of hyperparameters, train your model, and validate. So you can use this validation set for selecting which set of hyperparameters should we keep. But the structure will be the same because we agreed already on the structure. When we build our model, we agree on a structure, and we will use the validation set for adjusting those hyperparameters. So I mean, this is the idea behind having a validation. Yes?
Just one question. So about this this momentum term, is it, the question is, so let's say in case of an MLP, I train my MLP with some data, and then I am not happy with the results. So I include more data, and then I retrain my MLP. So will the first training will have any effect on my second training, or is it they're totally independent? Will this momentum term like have any effect on? Did you get my question?
Yes, it will have an impact. I mean, it's according to how the error function looks like, right? Might be you don't need it. If your cost function looks like this one, for example, I don't have any bumps. I don't have any global local minimum. So in this case, I don't need effect, right? And if you introduce the momentum term, maybe it will help you, maybe it will not help you, right? So no one knows. I mean, it's a hyperparameter. You need to try, in fact. So once you build your model,
this memory is internal to the model, or
no, it's internally. It's in the training process, and then when you finish it, it's finished. I mean, it's in each step. When we use in the training process, it just memorize something from previous training steps. So you can remember 2 steps back. You can remember 5 steps back. You can remember 10 steps back. So it's just a memory. It's internal memory in the
okay.
This gradient
which means that my training 1 with like data 1 will not have any effect on my training 2 with data
yes.
1 plus something, right?
No, not at all. It's
so
only,
this is a finished model.
Yeah, if it is a stochastic gradient descent, for example, right? If it is stochastic, so in this case, I will remember the previous example or 2 examples, right? If it is batch gradient, so it has no, I mean, it's just a step. I mean, the last step, what was the last step? I don't know how can we do it in batch gradient, in fact, because it's independent. I mean, we do it in, yeah, maybe because in batch gradient, it will remember something from the last epoch, maybe, correct? So in batch gradient, it will remember something from the last epoch. But when it's stochastic gradient, we will remember something from the last examples, the last 2 examples, for example. So you just, I mean, for us, in fact, it's just a momentum term which will give us more power to just, do you know, when imagine you are driving an old car and you have like a bump, for example, and you just need someone to just push you away, give you some force to just avoid this local minimum. So this is the idea behind this momentum term. Yes. So back propagation, I mean, this is the task for us, in fact, to study back propagation or error back propagation. So in many machine learning applications, we find good model parameters by performing a gradient descent. When it's straightforward, we call it error back propagation. So this is the model which we will try to develop for it today. So this model, it's a sample. We have one input layer. We have some inputs connected in this input layer, we have 2 inputs, 3 inputs, for example. We have one hidden layer, and we have an output layer, right? In this error back propagation algorithm, we'll go forward for calculating the outputs. How can we do it? So it will be x will be a vector, right? So x here, it will be a vector. So if I want to do it, so because calculation, it's when it's in there, it will make life much easier. So x will be like this one. So this is input x equal x1, x2, right? But remember, we have +1 here. This +1, it's a bias. So if you want to do, so I can just add +1 here. So if you want to add +1 here, it's okay, because this one, it will be for the gradient. It's like an input for the gradient. So the weights, because I can do it for, we can do it simple. I can just do it for the weights, and after that we can do it for the bias. So this is the x. This is my input vector x1 and x2. This is one example. So if we are working for a problem for credit scoring, for example, maybe this is my age, this is my income, correct? If it is M-nested data set, it will be pixel value. X1 and x2 will be pixel values, right? So the weights, we will have 4 weights. So omega will be, could be omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. Just, ignore bias now at the moment. If I want to find the input, or the output, so it will be x, omega x plus bias. So I will just find this net. This net, it will be omega x plus b. We should get 2 outputs here, correct? So omega x, so it will be 2 plus bias. Bias, it will be a vector also b1 and b2, correct? So if you want, I can just, I don't want to write it one more time, but it's okay. It will be omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2, multiplied by x1 and x2 plus b1 and b2. So this one, in fact, it will be net 1 and net 2. So it will be 2 times 1 vector. So this is the output here, correct? So now we have net. So now I need to apply the cost function. So the cost function, the activation function, maybe it's y equal 1 plus divided by 1 exponential minus net. So we will just apply this one here. So we will get y1 and y2. So now we have y1 and y2. So just matrix notations. I did that for this layer. We will do it again for the second one, just exactly the same. It's a similarly here. We have y1, y2, b11, b12, b21, b22. We will just apply it. We will get the outputs here. Apply the cost function, any cost function, it will be ReLU, Gaussian function, hyperbolic tangent function, any function, we don't care. So in fact, we have the input vector multiplied by this matrix, which is the weights. We will get the summation here. This is the summation here. Apply this summation value to the activation function. We will get the output here, and we will just do this step by step, just for each layer, until we get y1 and y2. y1 and y2, this is the predicted output. This is the predicted. But I know that there is something here, target value and the target value 1, and because we have 2 outputs, correct? 2 outputs. So maybe I have, maybe this one is 2 classes, right? Maybe this is the one we should get alone, this one should not get alone. When it's 1 here, it means it's 0 here, right? So I have T1 and the T2, correct? So we will calculate the error. So the error will be like this one. So the error will be, it's half summation T minus Y squared, right? Correct? So now I need to go backward. We will calculate this error value. We don't need to calculate it, in fact. This is the function. We just need to find the formula for adjusting the weights. Now I need to adjust delta V and we need to adjust delta omega, correct? We need, it will be the same also for delta B. Don't worry about delta B. Delta B will be the same, but without, I mean, because the function, I mean, it's not function of B. Anyway, we will just do it step by step. But I can go for this one. So we will calculate the error function. Of course, it's tk. Why it's tk? Because maybe I have two outputs. It will be t minus y if we have only one output. Tk, we need to use this notation if we have two outputs, three outputs. So we need to differentiate between it. So it could be tk where k equal 1, 2, 3 number of outputs, or b, for example. So so delta v, I will start with delta v. Delta v will be minus eta partial e by partial v. Delta omega, it will be the same, minus eta partial e by partial omega. So now we need to calculate this first value, partial e by partial v, right? How can we do this? So partial e by partial v, this one, it's function of y, correct? Error is function of y, but it's not function of v, right? So we need to find any connection. We use something called the chain rule, because we need to reach this one. We need to find this one. So we will start with this one first. We will start with this one. I will get first partial e by partial y, because I can see y here. So I can get partial e by partial y multiplied by partial e. It will be also partial y by partial what? Y is function of net. First, yes, it's a partial of omega, but if we will use this Gaussian function, for example, so I can just say y equal 1 plus exponential minus net. And remember, net equal omega x plus b. So we will do it from here, because I cannot go from y to net directly in one step. We need to make it simple. You can go directly to y, but it will be more complex. So it's easy to just go by partial y by partial net first. And after that, from partial net by partial omega. And by partial net by partial b, right? Because we have a bias. If you want to adjust to omega, I want to get partial net by partial w. If I want to adjust to the bias, I need to get partial net by partial b. Partial net by partial b, it will be 1, right? But partial net by partial omega, it will be x. So when you're adjusting the weights, you need to put this one equal x. This one, it will be x or 1. X when we're adjusting omega, and it will be 1 when we're adjusting the bias. So when we're adjusting the bias, it will be the same equation, but it will be more simple, right? So now we need to find first partial e by partial w. It's easy, right? What is partial e by partial y? Can you take the first derivative? It will be 2 times this one, 2 times half, it will be 1. So it will be t minus y multiplied by partial t, which is 0, multiplied by partial y minus y, will be minus 1. So in fact, I can just write partial e by partial y, it will be 2 times half, which is just 1. So it will be t minus y, because it's a 2 times, I still need to subtract 1 from this one, it will be 1. And multiplied by the first derivative of what is inside. What is inside, it will be minus 1. So it will be minus 1. Or you can just make it simple, y minus t. Right? So this is the first one. Right? So what about the second one? I need to find partial y by partial net. It's very easy. Do you see? Partial y by partial net, it's y dash. Right? And I have the, I mean, how can I get it here? So this is the function here. This gx or yx, this function, if I want to find g dash of x, which is the first derivative, it will be minus 1 times, it will be minus 1 multiplied by that part, and subtract 1 from this one, it will be minus 1 minus 1, it will be minus 2, multiplied by the first derivative of what is inside it. So this one will be 0, exponential minus x, it will be minus exponential minus x. And just to try to simplify it. So at the end, it will be gx multiplied by 1 minus gx. So it is Gaussian. So this function is very important. I mean, when you select when you select the activation function, you need to select one which you can differentiate. Now we have lots of tools, but for example, when I did my master degree a long time ago, it was in 2002 or something, we don't have those Python stuff, and even MATLAB, we have to do it in C++, in fact. So at the time, it was important that you do it analytically and you do it by yourself. So it was important to select a function which can easily differentiate it, right? So now we need to get partial y by partial net. In fact, it will be y times 1 minus y, correct? Look, there's the last line here, g dash equal g times 1 minus g. So this is the partial y by partial net. What is else? We need to get partial net by partial omega. Okay, net equal omega x plus b, right? Net equal omega x plus b. Partial net by partial omega is just differentiate for omega. Omega x, what is the differentiation of omega x? It will be just x. Because differentiation for omega, it's like 2 omega. So it will be just 2. Because x is constant and the b is constant. So it will be just x. So partial net by partial omega, it will be x. And if you want partial net by partial b, it will be just 1. Right? Because this is a function here. I mean, omega x plus b. What is partial net by partial b? Omega will be constant, x will be constant, so it will be just 1. So this is the function. We call it chain rule. Chain rule because I want to, this is the chain rule, partial e by partial y by partial net by partial y. So at the end, I got partial e by partial omega. We call it the chain rule. So now we get the formula. Now, if you want to put it in the code, so I can just say, okay, delta v, right? You can just call it delta v by g, or right? Because it will be different. Which one is connected? Because if I'm adjusting delta v, this one, we will use this y, correct? If adjusting this one, which is connected to this one, I will use this one. So that, I mean, notation is very important, right? So the notation is very important. So, but we can make it easy. They calculate delta y. We calculate delta y here, right? What is delta y? They just try to make it simple. Delta y, in fact, it's partial e by partial net. They call it delta y. Partial e by partial net. So I can just call this one delta y. So we will have delta y1 and the delta y2 if you want to make it as a vector, right? If you want to call it. So anyway, I can just write this one as minus. Of course, we have minus multiplied by minus eta. Do you remember? We have minus eta. So minus minus, it will be plus. So it will be eta t minus y multiplied by y times 1 minus y multiplied by input. What is the input for this one? The input for this one, it's h1, correct? So multiplied by h. Multiplied by h. If it is delta v, it will be the same. But instead of multiplying it by h, it will be multiplied by 1. Right? Because the input for the BIOS is plus 1. Right? If you want to make it easy, you can just combine this one. I mean, usually they combine this one and they call it delta. They combine this one and they call it delta y. And we will have delta y1 and the delta y2 because we have here 2 outputs. So delta y1, it will be t minus y1 multiplied by y1 times 1 minus y1. So you will just do it like this. And if you want to adjust the weights here, we will do it for this one here, right? We will do it for this one here. So we will get partial e by partial omega. We got here partial e by partial v, correct? We did here partial e by partial v. If we need to do it for, so finally I will have this, you see? So we will get this is the error. Partial e by partial y, we got this one, right? This is the function. This is the first derivative of the function, partial y by partial net. So I will get this net. It's v times h. I mean, Of course, it's V times H. I call it X, but X for this one, it's H. So it will be like this one. So this portion net or portion V, it will be the input. So I will call this one delta Y. So delta Y, it will be partial E by partial net. So it will be this formula. So at the end, we will have this delta V GK. It will be minus eta learning rate multiplied by delta YK. Right? Delta YK multiplied by HG. Right? As the input. If it is for bias, it will be minus delta minus eta multiplied by delta YK directly. Right? And similarly, we can do it for delta YIG. So I want to open the code and show you the code. So this is the code which I did. You can go for, for the implementation, you have, yes, this one. It's EPL. Error track propagation. So just go for it and try to open it from GitHub. And I did it for this example. I did it for Iris dataset. In Iris dataset, we have 4 inputs. We have 4 features: Symbol length and width, and beta length and width. So we have 4 inputs, and I used one hidden layer for 4 units. And the output layer, of course, we have 3 classes. So the output layer has 3 outputs. And I use the Gaussian function. So I can go back to the code and show you. Implementation, it's simple. Here, I started by just initializing the weights. I just uploaded my data set. This one, it's just uploading your data set, in fact. So divide the data into training and testing, and uploading your data, normalizing it, fixing it, right? And after that, I have the weights. So the weights will be, for the first hidden layer, You have a question?
No.
Okay, so it will be number of features times number of hidden units. The weights, number of weights, number of omega values. It will be number of features multiplied by number of units in hidden layer. The bias, it will be number of units in hidden layer. Right? For the output layer, it will be a number of hidden layer units multiplied by number of classes. And the bias of the output layer, it will be number of classes. And I just initialized it, and I put it in this for loop. And I just implemented SGD, stochastic gradient descent. When it's a stochastic gradient descent, it's quite simple. We do it example by example, right? But we did an implementation before for batch gradient. You remember? We did implementation for batch gradient. So first we will go forward. We will calculate net H. So it will be X times omega plus B. This one, it's just X times omega plus B for the first hidden layer. So we will get net H. Now I need to get the output from this layer. It will be 1 divided by 1 plus exponential minus net. Right? So this is straightforward. We use this Gaussian function, and it's 1 divided by 1 plus exponential minus net for the other layer. So now we are going forward. So when we go forward, we calculate net H, output from H, and the net O and the output. This is the output. So the output here, it will be the output from here multiplied by the weights plus the bias for this layer. And after that, I will apply this function 1 divided by 1 plus exponential minus net. So now we go forward. When we go forward, we calculate the output, right? So when we calculate the output, we need to go backward. How can we go backward? I need to the battery just lost for and they claim, when you buy a laptop, they claim that it can work for 10 hours. So
it's under optimized conditions.
Yes. Because the new Mac, last year, I guess, Apple, they have this new Mac, MacBook Pro. As you said, it's 10 hours. So some colleagues, they bought it and we tested it. In fact, it's maybe 3-4 hours.
Yeah. It's only 10 if the screen is off. and
everything is off.
Yeah.
When everything is off, it can last for 10 hours.
Yeah.
Yeah.
This is a good selling point. It's
Yeah.
the selling point.
Yes, because 10 hours, it's a very good. You can just travel without carrying power cable and
you got power range.
yes. So do you have the slide in the Blackboard? I don't remember if I put this one in Blackboard. No?
No, it's
okay. I will upload it to Blackboard so you can go to the code, but I want to explain this code first. So now we go forward. When we go forward, we calculate the output. And after that, we need to go backward. When we go backward, first we need to find delta O and delta output and delta H. You just call it anything. So I need to find this delta O. So the delta O, it would be output minus T. Do you remember y minus T? So it would be y minus T times y multiplied by 1 minus y. And after that, I need to calculate delta H. So delta H, in fact, how can I get delta H? It would be omega multiplied by delta. So it would be this omega values multiplied by this delta. Delta H, it would be this value multiplied again by y times 1 minus y. I put it in 2 lines to make it easy. So it's omega multiplied by delta multiplied by y times 1 minus y. And after that, adjust the weights. Adjusting the weights, it's simple because omega equal minus eta multiplied by omega multiplied by x multiplied by delta, right? So it's this one, it's x times delta. And for the bias, it would be just eta multiplied by delta because we don't have x. X for bias is 1. And we will do it for the other layers. And this one, it's just for, evaluating after each epoch. I used here, in each epoch, we make this evaluation, we predict for x because I need to plot. So for each epoch, after each epoch, I will apply the X train. I divided also the training data into one for training, one for validation, in fact, and one for testing, because we have 3 sets. We should plot 3 curves. And it's important to have training and validation because you can, maybe the lecture for next week, we need to check if we have overfitting. Because overfitting, it's crazy. It's a very hard problem, in fact, when you have overfitting problem. How can we discover overfitting? From the loss for training and validation, or accuracy for training and validation. You will see at the beginning that all numbers are fine, it's going down, but suddenly the validation set, it will go, loss value will go up, right? It will keep decreasing for training, but for validation, it will go up. Which means my model now started to memorize my training data, and he knows nothing about the validation, he cannot generalize. So we can discover this from those curves. So I did it and I plotted for, maybe you have also here some overfitting problem, but I can reach an accuracy of 90% using my simple model. We used only one hidden layer of 4 units. So the simple model, very, very simple model. We have 4 inputs, 1 hidden layer of 4 units, and the output layer has 3 outputs. So this one for testing, this one, it's the accuracy. So it goes up, right, from epoch 0. Right? And it continue going up. The most important is the validation, in fact, right? So the validation here, it's also okay, right? And this is for testing. Okay, training. The training is the blue one. The blue one, it's a training, and the green one, it's for validation, and this one, it's for testing. So it's very, very important because you need to tune your model according to those numbers. If you feel that you have some overfitting, you need to stop. We should not continue training our model if we have overfitting. I will upload this slide into Blackboard so people can just play with it. And please go to the code, try to change it. Maybe try to add one more hidden layer, right? And just to check it if you have any question, we can discuss it. So in this graph here, in fact, when we calculate delta x here, we calculate delta here. We need to calculate delta for this layer. Delta here, it will be omega multiplied by delta, because we need to go backwards. Because in fact, each delta here, it came from contribution from each one of those. This weight value will contribute to the delta value here. This one will contribute to it. This one will contribute to it. So in fact, I mean, the weight values here, they are in charge also of developing this delta value. Delta value, it's error value. So if I need to get those values back here, I need to multiply it with the weights, right? So this one here, I have 3 values, and the weights here, it's 4 times 3. So just to transpose omega, multiply it by delta values to expand it to 4 values here, right? So it will be 4 times, I mean this matrix, it's 4 times 3 times this vector, which is 3 values, you will get 4 values here. And after that, multiply it by partial y by partial net, which is y times 1 minus y. So when you implement it by step, you really. So I will upload the slides to Blackboard. So okay. So please go to Blackboard and try to download the slides to your computer and try to work with the example. This one, lecture number 6. So you have it in Blackboard now. So just please try to open it and use the link for this GitHub and try to change the code. And if you have any questions, just let me know. And we can take a break and maybe start after 10 minutes or 15 minutes. Is it okay online if we can go for a break? You have the slides uploaded to Blackboard now, so please just go to it and try to open the code and try to play with it, try to make some changes. We don't have here momentum term, for example. You can add momentum term to this implementation. You can also add more hidden layers. I mean, now I have a simple function. I can open it, in fact, and I can show you the code. So, I cannot find my notes. So I will share this one. It was better to get my mouse. So can you see my slides? Maybe not. Can you see this one? No.
No, not on.
Okay.
We can see a blackboard and we can see your camera.
Yes. This one?
Yeah.
Okay. So this is a code, in fact. So we start by just defining a function. I call it feed forward, and we need to define here eta, learning rate, number of epochs, number of hidden layer, number of units in the hidden layer, because we have only a single hidden layer. So by default, I selected 10, seed, maybe shuffle, validation set, and test set. So if you have your data, maybe 20% will be used for testing, the 20% will be used for validation. So what is remaining is 60% will be used for training. So I define the eta, number of epochs, number of hidden layers. So just it's something standard. For evaluation, I will have training accuracy, validation accuracy, and test accuracy. I will shuffle. If we need to shuffle my data, it's important to be sure that, because if you are using a sklearn function, this training test split, it automatically shuffles the data. But here we need to be sure that it's shuffled, because Iris dataset, it's 50 examples for first class, another 50 and another 50. So we need to shuffle it. And after that, we will just initialize our weights. We initialize the weights and we initialize the weights and okay. So we initialize our weights here, right? And apply SGD. So if you want to do it for, you can try, in fact, you can just try to make it mini batch or batch gradient, for example. If you want to change this one into batch gradient, so I need for going forward, we will get, you can make this one as a function, for example, because now we don't want to do it example by example. So you can just make it as a function, and you can send all x train one time, calculate the gradient one time, and they use a average gradient for adjusting the weights. So instead of doing it example by example, we will do it in each epoch. So this one for predicting. For predicting, it just does copy from this one, in fact. So I just copied that part. Do you see updating weights here for output layer? I just did it here one more time. And the output will be number between 0 and 1. Do you see? This output, it will be, I'm using a Gaussian, and this Gaussian, it squash inputs into number between 0 and 1. So the output will be probability between 0 and 1. So I need to get the maximum. I need to decide which class. So I just used argmax. So because I need to decide in which class. The output. Each example should belong to only one class. So I just used this function for the output here. So this is one will be the output. And after that, I just this is my function, and I got my Iris dataset from sklearn datasets. And this is my function feed forward. I used here feed forward. But first, I normalized my data sets. So I got x from here, and I normalized it. So it will be x minus minimum divided by range. Scaling, this is standardization, or you call it normalization, for example. And y will be this iris.target. This output value, it will be, in fact, only one column, 0, 1, 2. 3 classes. So you can use one hot encoding. You can use one hot encoding for maybe it's a 3 values. In fact, maybe it's already in one hot encoding, because no, maybe I used here one hot encoding. Maybe. Yes, I used it here. 2 categorical. We will need to convert it to one hot encoding, so I used this function here. So I converted it into number of classes, 3 column, right? So, and I got this one. Also, accuracy is 26%, which is very good accuracy. But of course, we should reach maybe 99%. I mean, we did that before, and we can get 99% accuracy. So if you want to run it, so you can go to this option and you can just try to make some changes. Make it for batch gradient, mini batch gradient, add momentum term, for example. So you can just make it more. So, I mean, we will get the same accuracy, 19.6%. Because I'm using random seed. I'm using random seed here. See? Yes, so I mean, if you will change the random values, you will get different values. You see, now we need more time, in fact, for training our model. Maybe 100 epoch, it's not very enough. So the accuracy now it's 69%. Because as I told you, I mean, the curve is bumpy. We don't know, we cannot guarantee. I don't know how the curve looks like, but maybe here we stuck in local minimum and we need more epochs, in fact, so maybe we can repeat it using maybe 200. I mean, it's very quick. Just use 200, for example, and run it one more time. So it's improved, which means we need more time for training. Could be like, yes, so now we can reach 90% accuracy. Maybe it's underfitting for data because the model is simple. Maybe we need more hidden layers. Maybe I'm using here 4 units. I'm using here 4 units as hidden layer. Maybe we need more, right? Could be 10, for example. It could, I mean, improve the. You know, it's 94%. So I mean, those hyperparameters, we need to adjust those hyperparameters, and we need to. So in this example, for example, you can just make it more complex. You can add the gradient descent. Sorry, you can add, I mean, batch gradient, for example, mini batch gradient, and add momentum term. We didn't add momentum term. So. So any question? Or, anyone has any question online or something? I guess we have lots of questions, but I didn't look into it. Okay. Yes. So we will take a break now. We will take maybe 10 minutes or 15 minutes break, and we will start again after the break. Yeah.